Welcome back, viewers. In today's lecture, we shall talk about the characterization of supremum of subsets of R that are bounded above. Recall that in the last lecture, we ended the last lecture by looking at the characterization of infimum of subsets of R that are bounded below. Before we start, let us recall that a subset E of R, of course we require that E is non-empty, is bounded below if there exists theta in R such that for any x we pick in E, theta is less or equal to x. And the set E is bounded above if we can find gamma in R such that for any x we pick in E, x will be less or equal to gamma. And then we say that E is bounded if E is bounded both below and above. These are part of what we saw in our last lecture. And in that lecture, we remember we made you to understand that once a set is bounded below by, say, theta, then it is bounded below by all numbers less than or equal to theta. And if a set is bounded above by gamma, then it is bounded above by all numbers that are greater or equal to gamma. So assuming that here is theta and somewhere here is gamma, and the set in question is this portion of R, not necessarily an interval, then we say that the set E is bounded below if we can find this theta in R, so that for any x we pick in E, theta will be less or equal to x. And is bounded above if we can find gamma in R, so that for any x we pick in E, x will be less or equal to gamma. Any other number bigger than or equal to gamma will also bound E above. And thus, if we the number gamma we require is an upper bound, while theta is a lower bound. So all numbers bigger than gamma are all upper bounds. And thus, you recall, we said that it then makes sense to talk about an upper bound that is nearest to E. And that upper bound that nearest to E is the one that we are interested in. I could remember jokingly saying that that upper bound and the lower bound that are closest to E are the meat in the soup we are cooking. What is the soup we are cooking? We are cooking the soup of trying to make listeners understand properly the concept of the greatest lower bound and the least upper bound, the concept of infimum and supremum. So in today's lecture, we pay more attention on the concept of supremum, and we'll go straight to the characterization. Now, let E be a non-empty subset of R which is bounded above. Then a number theta, or rather let me say a number gamma naught in R is called the supremum. Supremum, or least upper bound, or least upper bound of E written gamma naught equals sup of E if and only if I, for any x we pick in E, x is less or equal to gamma naught. Number II, if gamma in R is such that for any x in E, x is less or equal to gamma, then gamma naught must be less or equal to gamma. This actually is what makes gamma naught the least upper bound of E, or the supremum of E. That is to say that if gamma is any other upper bound of E, then gamma naught must be less or equal to gamma, meaning that the gamma naught is smaller than every other upper bound of E. The first one is telling us that gamma naught is an upper bound of E. This one is telling us that it's smaller than every other upper bound of E. As I put down all these things, try to compare with what we did, or rather what we saw when we looked at the characterization of infimum of a subset of R that is bounded below. This is the one way of seeing gamma naught as the supremum of E. Alternatively, gamma naught equals supremum of E if and only if I is always there, because I is telling us that gamma naught is an upper bound. That is if and only if for any x we pick in E, x is less or equal to gamma naught. And for any positive number you give me, for any epsilon bigger than 0, gamma naught minus epsilon, gamma naught minus that positive number, epsilon, is no longer qualified to be an upper bound. Gamma naught minus epsilon is not an upper bound. Is not an upper bound of E. So what we are saying is that once gamma naught is the least upper bound of the set E, then if you remove a positive number from gamma naught, no matter how small or big that positive number is, with the new number you will get, that is gamma naught minus epsilon, is no longer qualified to be an upper bound. Then still an alternative way of seeing this, I'll still say alternatively, gamma naught equals supremum of E if and only if I, for any x we pick in E, x is less or equal to gamma naught. And for any epsilon bigger than 0, there exists a y epsilon in E, y depending on epsilon in the set E, such that gamma naught minus epsilon is really less than y epsilon, and y epsilon is less than or equal to gamma naught. So this is saying that if gamma naught is the supremum of E, then we can find an element of E, for given any epsilon bigger than 0, we can find an element of E depending on that epsilon, so that this inequality holds. Now, this can be likened to the diagram we drew when we are looking at the case of infimum of a subset of R is bounded below. Assuming that this portion of the line, not necessarily an interval, represents the set E that is bounded above. This is E that is bounded above. And assuming that somewhere here is the gamma naught that we are looking at as the least upper bound of E, or the sup of E. What we are actually saying, just like as I depicted in that lecture on infimum, that assuming that someone stands here, this time around stretches his or her leg backwards and covers, say, a distance epsilon, then that, since the person is making a backward movement and covers a distance epsilon, the new position where the person's leg will fall will be at gamma naught minus epsilon. And on getting at this position, for the fact that gamma naught minus epsilon is no longer qualified to be an upper bound as we stated here, then there must be something here that lies in between the person's leg. That thing that lies in between the person's leg, call it x epsilon. And that particular x epsilon is a member of the set E. And is such that is less or equal to gamma naught, but strictly greater than gamma naught minus epsilon. As I mentioned in the case of infimum, this inequality is very important and must be remembered as it appears. Here is not strict. Here is less or equal to, where here is very, very strict inequality. Now, again, as I mentioned there, the next characterization involves a sequence of real numbers which we've not introduced. And what it says is that whenever gamma naught is a supremum of a given set A that is bounded above, then we can find a sequence in the set that converges to gamma naught. So when we introduce the concept of sequences of real numbers, definitely I'll come back to this characterization and make it clear. Now, having put down the characterizations of the supremum of a subset of R that is bounded above, I think maybe we'll take some examples. We'll look at some examples. Now let us look at the following example. Let us look at the following example. Let us consider this set. Observe that, I want us to observe that for any x we pick in that particular E, x is less or equal to 5. X is less or equal to 5. And given epsilon bigger than 0, we can say that we can find, say, y epsilon, which are level 5. In what? In the set E, so that 5 minus epsilon is less than y epsilon, and this is less than or equal to 5. This is a true statement, and this therefore means, by the last characterization, that gamma, if we say gamma naught equals 5, then it means that gamma naught is the supremum of this set E. Gamma naught equals 5 is the supremum of this set. So with this, I can conclude, therefore, that 5 is equal to the supremum of the set E. 5 is the supremum of the set E. Now, another example, maybe let me call this one example 1. Then we look at example 2. Example 2, let us consider a set. Consider the subset E of R given, if we look at that set, I would like us to, in this case, let us show that the supremum of this set E is equal to half. We want to show that the supremum of this set is equal to half. Remember, to show that the supremum of this set is equal to half, we must first of all show that half is an upper bound. Remember, we have about 3 characterizations on the board now for the that is characterization of the supremum. Any of them can be used, but since they are all equivalent, I will be using any one of my choice. But the most important thing is that the listener should note that all of them are of equal importance. We must remember them because any of them can be used at any time. The nature of the problem being solved will determine the one to be used. So, and of course, we can see clearly that the last one is a clear representation of this second to the last. So let us see how we do this problem. So, solution to, we want to check that the supremum of the set E is equal to half. Is equal to 1 over 2. So how do we do that? First of all, we shall, let me put question mark here because question mark means we are trying to establish that the supremum is not yet established. So I put it as a question mark. So solution to this problem, we do it in stages. The first stage I'll call I. The stage I is to check that half is an upper bound. And to do that, we must show that for any x we pick in E, we must have that what? That x is less or equal to half. So this is what we want to first of all check. That given x in E, x must be less than or equal to half. Now, but x in E implies that there exists, or rather x in E is equivalent to saying that there exists a certain number n depending on x in the set of natural numbers such that x is equal to nx all over 2nx plus 1. What this means is that every member of this set must be of this form, of the form n all over 2n plus 1. Therefore, looking at this, we see that x equals nx over 2nx plus 1 is actually less than or equal to nx over 2nx. This is true because the denominator in the first quotient is heavier than the denominator in the second quotient by 1. Or rather, let me put it, okay, let me say, I will explain. So this is less or equal, which is now, this particular one, this we, of course, we cancel to give us, and cancel this, and this gives us half. So what this means is that for any x we pick in E, x is less or equal to half. But how did we get this? From that, let me put it aside somewhere here. Remember that nx, 2nx plus 1 is of course greater than or equal to 2nx. This is a true statement. This is true. That 2nx plus 1 is greater than or equal to 2nx. This we know. And we know nx is coming from the set of natural numbers and therefore is non-zero. And this means that these two entities are positive entities, and thus I can take reciprocal here. If we take reciprocal, we'll get that 1 over 2nx plus 1, 2nx plus 1 will be less or equal to 1 over 2nx. Then multiplying both sides by nx, we get that what? Nx, therefore, nx over 2nx plus 1 will be less than or equal to nx over 2nx. And this gives us nothing but 1 over 2. That is the idea behind getting that this happens. So what we've achieved now is that half is an upper bound of that set E. Now the next thing we shall do is to look at here. We let epsilon bigger than 0 be given. The next job we should do is we find, say, x epsilon in E. Remember that our E is of the form n over 2n plus 1, so that n is in the set of natural numbers. So we shall find x epsilon in this set such that half minus epsilon will be less than x epsilon, and this will be less than or equal to half. This is what we want to look for. But as I stated before, if x epsilon is in E, this will be equivalent to there exists n epsilon in the set of natural numbers, so that x epsilon is equal to n epsilon over what? 2n epsilon plus 1. So whatever we are looking for, this x epsilon we are looking for must be of this form. Must be of this form. So finding x epsilon in A is equivalent to finding n epsilon in N, for which this will happen. So what this means is, therefore, we shall actually find n epsilon in the set of natural numbers such that half minus epsilon will be less than n epsilon over 2n epsilon plus 1, and this will be less or equal to half. This is what we want to achieve. But here, we have to be very careful. We already know that from here, that for any x we pick in this set, that x is less or equal to half. So if we find such x epsilon in this set, already by the above, x epsilon must be one of these x we've seen that are less or equal to half. Therefore, x epsilon must be less or equal to half. This means naturally that this inequality already holds. So the one that will give us the n epsilon we are looking for is this part of inequality. So this looking at this inequality will enable us to get the range of n epsilon, n that will do this job, that will solve this problem. So we shall concentrate on this inequality to find this n epsilon. And once we get the range of the n epsilon, we can choose any of them, and that will do the job for us. So what we shall now do is we compute as follows. We compute as follows. I want us to observe that half minus epsilon less than n epsilon over 2n epsilon plus 1 less or equal to half implies that half minus epsilon is really less than n epsilon over 2n epsilon plus 1. So this is true. And what does this mean? This in turn implies that 1 minus 2 epsilon over 2 will be less than n epsilon over 2n epsilon plus 1. And to clear fraction, having non-negative terms, or rather positive terms in the denominator, we multiply both sides by the LCM of the denominator, which is multiplying both sides by 2 times 2n epsilon plus 1. So this will mean, therefore, this will imply that 2n epsilon plus 1 into 1 minus 2 epsilon will be less than 2n epsilon. And we do this algebra to get that, place this to be in bracket. to get that 2n epsilon minus 4 epsilon n epsilon plus 1 minus 2 epsilon will be less than 2n epsilon. Will be less than 2n epsilon. Of course, looking at these two sides, you will observe that there is 2n epsilon this way and there is 2n epsilon this way. And if we subtract 2n epsilon from both sides, we'll get that this and this will cancel out. So that what remains will be that minus, this will imply that minus 4 epsilon n epsilon plus 1 minus 2 epsilon will be less than 0. That is subtracting 2n epsilon from both sides. And from which we'll get that minus 4 epsilon n epsilon will be less than minus 1 plus 2 epsilon. Now, multiplying both sides by a minus 1 will give us that 4 epsilon n epsilon will be greater than 1 minus 2 epsilon. This is true, and from which we get therefore that this implies that n epsilon is greater than 1 minus 2 epsilon all over 4 epsilon. So what are we talking about? What we are saying is that given epsilon bigger than 0, whenever we are giving epsilon bigger than 0, to find n epsilon in the set of natural numbers for which this inequality will hold, we need to do these algebraic manipulations. And after doing that, we'll get this range. So what this means is that whatever epsilon bigger than 0 is, whenever we evaluate this number, any natural number that is bigger than this number can serve as n epsilon. Any number that is bigger than this number can serve as n epsilon. And once you get that n epsilon and walk back, you will observe that this inequality will hold, and which will eventually give us that this holds. So once we choose n epsilon bigger than 1 minus 2 epsilon over 4 epsilon, then we are done. So what are we saying? Assuming that here is the real line, assuming that here is this is the real line, and assuming that 1 minus 2 epsilon over 4 epsilon is here. So what we are saying is that any natural number that is above this will do that job for us. So at times what we need is choose any of them. At times what I do is you choose the one nearest to this. Now, how do we see this clearly? So what we are with this thing is that any n that falls this way, any n epsilon that falls that to the right of 1 minus 2 epsilon over 4 epsilon, we do the job, because this n epsilon will require to be greater than this. So any n once it's for any natural number that falls within this side, will do the job. For people to appreciate what we are talking about, let us take a specific, here we require n epsilon to be greater than this entity. So n epsilon must fall somewhere here. Now for us to appreciate this, if we take for instance, let us assume that epsilon is, say, remember that epsilon is any number that is bigger than 0, so we can assign value to it for us to be able to do something. So if assuming that I take epsilon to be half, if I take epsilon to be half and I evaluate this thing, and I evaluate 1 over 1 minus 2 epsilon over 4 epsilon, you'll find out that this will give me 0. And if this is 0, it means that any natural number will work for epsilon equal to half. Because for epsilon equal to half, this entity becomes 0, and all the natural numbers are bigger than 0. So how is this 0? Substitute half here. This will give me 1 minus 1 over whatever, and that will give me 0. So for epsilon equals half, any n in n can serve as n epsilon in the above computation. Now, if epsilon is bigger than half, will mean that this number will be negative, will give us a negative number. And if this is negative, then any natural number will work for epsilon bigger than half. Any natural number will have for epsilon bigger or equal to half. So if epsilon is smaller than half, let us assume that epsilon is, assuming that epsilon is 1 over 100. Let us see what will happen. If epsilon is 1 over 100, then, let me say epsilon equals 1 over 100 implies that 1 minus 2 epsilon over 4 epsilon will be equal to 1 minus 2 over 100 all over 4 into 1 over 100. And this will give me nothing but 1 minus 1 over 50 all over 1 over 25. This is what we'll get. But 1 minus 1 over 50 will give us, this will be equal to 49 over 50 times 25 over 1. And this will give us nothing but 49 over 2. And 49 over 2 is nothing but 24.5. So if epsilon equals 1 over 100, this particular value will become 24.5. What we are saying is that for epsilon equals 1 over 100, we may choose n epsilon to be equal to, say, 25, because 25 is bigger than this. We may equally choose n epsilon to be 26, 27, and so on. Any natural number that is bigger than this will work. Any natural number that is bigger than that will work. How do we check this? What we are trying to check is that, look at this now. Our epsilon is 1 over 100. So let us do half minus 1 over 100. If we do half minus 1 over 100, you will observe that this is like half minus epsilon, when epsilon is 1 over, epsilon equals 1 over 100, implies that half minus epsilon will be half minus 1 over 100. And this is nothing but, and this will give us 49 over. Now, let us observe. Let's see what will happen when n epsilon equals 25. Observe that n epsilon equals 25 implies that n epsilon over 2n epsilon plus 1 will be equal to 25 over 50 plus 1. 25 over 50 plus 1. And this will give us 25. This will give us 25 over 51, which will give us 0.49, I think 0.4901960078, something like this. But the interesting thing here is we have therefore that 1 over 2 minus epsilon, which is 1 over 100, equals 0.49 is really less than 0.4901960078, which is equal to 25 over 2 times 25 plus 1. Remember, this particular one here, half minus 100 is nothing but, sorry please, here is plus 1 here. So remember that half plus 100 is nothing but half minus epsilon, with our epsilon equals 1 over 100. I mean half minus 1 over 100, not half minus 100. It is nothing but half minus epsilon, where our epsilon is 1 over 100. And this is nothing but, this 125 is n epsilon, so this is like n epsilon over 2n epsilon plus 1. So we see that when epsilon is 1 over 100, that half minus epsilon will give us 0.29. And the choice of n epsilon equals 25 did not fail us, because that choice gave us that n epsilon over 2 n epsilon plus 1 will give us 0.490196078, which is, of course, really greater than 0.49. And that gives us what we are looking for. So what this means is, therefore, what we have is, therefore, we can now conclude, therefore, that gamma naught equals half is equal to the supremum of the set E, where E is nothing but the set n over 2n plus 1, so that n is in the set of natural numbers. So this is the supremum. N epsilon, I mean half, gamma naught equals half is the supremum of this set. And you can see, as I said earlier, that to get the n epsilon that will work, we have to face this inequality. And there's one other thing I would like to point out here. You remember when we took epsilon to the half, we got that any n in the set of natural numbers can serve as n epsilon. And this came from the fact that we evaluated this and got that this will give us 0. But in actual sense, the thing came from the computation above, in the sense that when epsilon is half, half minus half is already 0. And since half minus half is 0, any natural number will satisfy n over 2n plus 1 greater than 0. So that is why we got it trivially true here when epsilon is half. Good. The other ones follow. See what happens when epsilon is 1 over 100. So once you take epsilon to be less than half, you do this kind of computation, you will get that n epsilon over 2n epsilon, once properly chosen, will be greater than half minus epsilon, as we've just done for the case where epsilon is 1 over 100, which is really less than half. But if your epsilon is greater or equal to half, you will observe that this entity here will give us a negative value, and therefore any natural number will work. So that is it for this particular example. Now, let us try to see if we can apply this example in solving a particular problem. Now, let us look at this, another example. I'll put it as an example. I want us to prove that the interval 0.5 is equal to the union n equals 1 to infinity of the intervals of the form 0, n over 2n plus 1. This is what I want us to prove. To prove that the interval 0.5 is equal to this union. So how do we go about it? To do this problem, let me put the proof here. To tackle this problem, remember that to show equality of two sets, you take an element in the first set, in which you can start from anywhere. Take an element in any of the sets and show that it belongs to the other one. That will mean that the one you've taken an element from is a subset of the other one. then return to the other one, take an element from it, and show that it belongs to the second one. Once you do that, it means that this will be a subset of this. So what we should now do is to prove that these two sets are equal. And then I will try to start with the one I feel that is that will be easily understood. Let's go this way. Let us first show that union n equals 1 to infinity of 0, comma, n over 2n plus 1 is a subset of 0 half. After which we now try to show that 0 half is a subset of the union. So to do this, let x be in the union n equals 1 to infinity of 0 n over 2n plus 1. Let x be this. So we show that x belongs to 0 half. And once we're able to show that x belongs to 0 half, then it means that this union is a subset of 0 half. Now, but x in the union n equals 1 to infinity of 0, comma, n over 2n plus 1 implies that, this is actually equivalent to there exists a certain natural number n naught in the set of, there exists n naught in the set of natural numbers so that x belongs to the interval 0 n naught over 2n naught plus 1. So what does this mean? This means that if x belongs to this union, then it means that x belongs to at least one of them. And to interpret that means that x belongs to this union if and only if there is a certain natural number so that x belongs to this. So this therefore means that this is still equivalent to there exists n naught in the set of natural numbers so that, so x belonging to this interval means of course that 0 is less than x, which is less than n naught over 2 n naught plus 1. And from the example 2 we did above, remember the first example I did, I labeled example 1. The other one should be example 2. This one now is example 3. So from that example 2, we know that this n naught over 2 n naught plus 1 is less than or equal to half. So this means that this will imply that 0 is less than x, less than n naught over 2 n naught plus 1, which is less or equal to half. From which we get that 0 is less than x, less than this first inequality is stronger than this, and therefore if this is less than this and this is less or equal to half, then this should play a part. So this means that x is less than what? Is less than half. So what we've gotten is that this implies that x belongs to the interval 0 half. And with this, what do we have? What we have therefore is that union n equals 1 to infinity of 0, comma, n over 2n plus 1 is a subset of the interval 0 half. What I want you to observe is for us to observe that this place gave us a kind of application of example 2. That is the exercise we did in example 2, in the sense that we go here on the basis that half is the upper bound of the set E in example 2. Meaning that for any n in the set of natural numbers, n over 2n plus 1 is less than or equal to half. That is how we got this. Now, to get the other side, so this means that we've gotten that this is a subset of this. Next, we show that 0 half, the interval 0 half, is a subset of the union n equals 1 to infinity of 0, n over 2n plus 1. We now show this. To show this, what shall we do? The same approach. To do this, let u be in the interval 0 half. We show that u is in the union n equals 1 to infinity of 0, n over 2n plus 1. This is what we need to show now. But u in 0 half is equivalent to 0 is less than u less than half. This implies that half minus u is greater than 0 because u is less than half. So, setting epsilon u equals half minus u, we obtain that epsilon u is greater than 0 from here. Now, what's the essence of this? Now, we recall that half from the example 2, the half is equal to supremum of the set n over 2n plus 1, so that n is in the set of natural numbers. If we recall this, then this means that I, for any n in the set of natural numbers, n over 2n plus 1 is less or equal to half. This we've already seen. And I, for any epsilon bigger than 0, there exists n epsilon in the set of natural numbers, so that half minus epsilon will be less than n epsilon over 2n epsilon plus 1, and this will be less than or equal to half. This we've already seen that is true from example 2. Therefore, so from II, we obtain in particular that for epsilon u equals half minus u greater than 0, that is this epsilon u, which is greater than 0, there exists n epsilon u in the set of natural numbers such that this inequality will hold, but for epsilon u. So there exists n epsilon u in the set of natural numbers so that half minus epsilon u will be less than n epsilon u all over 2n epsilon u plus 1. And this will be less than or equal to this will be less than or equal to what? Half. This is true. But what does this mean? This therefore implies that that half minus epsilon u is less than n epsilon u all over 2n epsilon u plus 1. So this is what we have from here. And this further implies that using the definition of our epsilon u, what we have that this is half minus u. So this implies therefore that half minus epsilon u, which is half minus u, will be less than n epsilon u all over 2n epsilon u plus 1. But what is it? If we evaluate this, this will imply therefore that u is less than n epsilon u all over 2n epsilon u plus 1. But where did we pick u from? Remember that we picked u from 0 half, meaning that u is bigger than 0. And since u is bigger than 0, I can now write therefore 0 is less than u less than n epsilon u all over 2n epsilon u plus 1, since 0 is less than u, from what we saw above, from our choice of u, because we picked u from the interval 0 half. What does this mean? This means that thus u belongs to the interval 0, n epsilon u over 2n epsilon u plus 1. And this interval, of course, is a subset of union n equals 1 to infinity of 0 n over 2n plus 1. So what have we achieved? What we've achieved, therefore, is that u in the interval 0 half implies that u belongs to the union n equals 1 to infinity of 0, n over 2n plus 1. So this means that that 0, half is a subset of union n equals 1 to infinity of 0 n over 2n plus 1. And having got this, having got before that 0, that this union is a subset of 0 half, and now that 0 half is a subset of the same union, we can now conclude, therefore, that 0 half is equal to union n equals 1 to infinity of 0 n over 2n plus 1. So I did this example for the listeners to see one way of using the concept of supremum to solve a given problem. You can see if one is not conversant with the knowledge, with what we've done, this problem will look innocent but crazy, because you may not know how to start and how to do this. But you see that our knowledge of half being the supremum of this of the set n over 2n plus 1, so that n is in the set of natural numbers, has helped us in proving that these two are the same. So I think we may stop this particular lecture here, hoping to see you in the next class. But in the next class, I think we'll pause for a moment in giving the lecture. We'll do more of exercises, try to solve some problems that will sort of cut across all we've done so far. We'll cut across all we've done so far. And once we get to where we are right now, we do more examples and more applications of the concept of infimum and supremum. Hoping to see you in the next lecture. Thank you so much for listening.